Hey guys, back with another video. In this short one, we will cover Clairaut's theorem. You may know this theorem as the mixed partial derivative theorem or the mixed derivative theorem, but regardless of the name, the theorem is the same, and it says that if we have some multivariable function, and I will say f of x comma y, then we will take its derivatives, so partial f, partial x, and then partial f, partial y, and now we will take its two mixed second order derivatives, so partial squared f, and then partial x, partial y, and then partial squared f, partial y, partial x. If these five functions are defined, so if they are defined on an open interval a to b, and are continuous on at a comma b, then what is the result? Well, what that means is that the partial derivative of f with respect to x and then y, so partial x, partial y at a comma b is equal to, well, that will be partial squared f of partial y, partial x of a at a comma b. So it basically says that if these five functions are defined on an interval and are continuous at a point, then it really doesn't matter what the order is that you take the derivatives in, as long as you take them in the same order if you are calculating the second order mixed partial derivatives. In other words, you can take the partial derivative of f with respect to x and then y, or with y and then x, and you will get the same answer. So I'll do a quick example, and I will do a pretty extreme example of how this can really save you a lot of time, energy, and effort on a test or a homework assignment or whatnot. So let's say that we were given some function z, and this is a function z of x and y, so x and y are the independent variables. Let's say that z is equal to, well, let's say y cubed plus y sine of y plus 1 over e to the y, and then plus 1. And then we will add to this x squared and y. Well, and then if we were given this multivariable function and then we were asked to find, okay, we'll find partial squared z, partial y, partial x. Well, before knowing Clairaut's theorem, when we saw this partial derivative, this mixed partial, we would say, okay, well, we need to take the derivative first with respect to y and then x. And you would notice that there are a lot of terms containing y in this function. In fact, on the left-hand side, we have this really crazy fraction here with y cubed and y's times sines and then plus 1s over e to the powers of y. So technically you could take this derivative with respect to y and then with respect to x. But knowing Clairaut's theorem, it's saying, well, if this function is defined, and we see that actually everywhere this function is defined, because even this crazy fraction on the left-hand side actually the denominator can't ever equal 0, because we have e to the y plus 1 equals 0, which means that e to the y would have to equal -1, and then we know that e to any power can't equal a negative number. So the denominator there would actually never equal 0. And we also know that if we were to take the derivative of this with respect to y, then what we would do is we'd say, okay, well, we would take the denominator, all right, and then we would multiply that by the derivative, so the derivative of the numerator, and I will just write the numerator using n, and then we would say, okay, well, minus, that would be low d high minus, that would be the numerator, and then times the derivative of the denominator, so denominator, and then that would be over the denominator squared. So it would just be over e to the y plus 1 squared. But since this can never equal 0, well, that means that this can never equal 0 because we're just squaring it. So even if we take the derivative of that, it means that the derivative is still going to be continuous. So we've basically shown now that the function is certainly defined, and that the partial derivative with respect to f or with respect to y is certainly defined, and if we took this with respect to x, it would also be defined because this would just cancel out. And then likewise, if we would just apply the same logic, then it would be pretty obvious that the second order derivatives would also be defined or on that interval, and likewise continuous. So given all that information, we can say, okay, well, instead of taking the derivative first with respect to y and then x, let's do it the other way around. So we will find first partial z partial x, and what this will equal to is, well, this big term right here will just cancel out, and we will take the derivative of this, and that will equal, well, that'll be 2xy. And now if we take the partial derivative of y with respect to partial z partial x, or of partial z partial x, then that will just equal 2x. And that was a lot easier than doing the quotient rule and probably another quotient rule, but we found the derivative, or the second order derivative of this multivariable function using Clairaut's theorem, and it's simply 2x. I hope you found this video helpful. Clairaut's theorem is going to be very important, especially when we start solving differential equations in the future, and we deal with exact equations and integral theorems as well. It's going to be really important that we know this theorem. So be prepared to use it in future videos. Once again, if you have any questions, please leave a comment below, and please subscribe as well to help the channel to grow, and I will see you in the next video.